In this video, we will be describing molecular orbital theory as it applies to heteronuclear diatomic molecules. Heteronuclear means that the two atoms involved in the diatomic molecule are different elements. When the combining atomic orbitals, those that we are mixing together for our molecular orbitals, are identical and of equal energy, the contribution of each atomic orbital to the molecular orbital is equal. This is what we were observing for the homonuclear diatomics, where we were combining two of the same elements together to make a diatomic molecule. For heteronuclear diatomics, however, we are combining atomic orbitals that are different types and energies. For these, the atomic orbital closest in energy to the molecular orbital will contribute more to the molecular orbital. The more electronegative an atom is, the lower in energy the orbitals are going to be. Lower energy atomic orbitals contribute more to the bonding in our molecular orbitals than do the higher energy atomic orbitals. Higher energy atomic orbitals contribute more to the antibonding molecular orbitals. We can also have non-bonding molecular orbitals that remain localized on the atom, donating its atomic orbitals. Let's now look at some examples. So for NO, nitrogen monoxide, we have a nitrogen atom on one side and an oxygen atom on the other. We have our atomic orbitals that we will populate with their correct number of electrons. So for oxygen, oxygen has 6 valence electrons. We put 2 in our 2s and 4 in our sets of 2p's. For nitrogen, nitrogen has 5 valence electrons, 2 of which will go in our 2s and 3 of which will go into its corresponding 2p. Now, because oxygen is more electronegative than the nitrogen, the energy of the orbitals for oxygen are slightly lower than that for nitrogen. That's the case of both the 2s and the 2p. They're slightly lower, which means that the bonding molecular orbitals in NO will have a greater contribution from the oxygen's atomic orbitals than from the nitrogen. The antibonding orbitals, however, will be the reverse case. The antibonding molecular orbitals will have a greater contribution coming from the nitrogen than from the oxygen. The way that we fill the middle is the same as we were using for the homonuclear diatomics. We count up the total number of electrons and then fill the middle with our total. So from the oxygen we have 6, from the nitrogen we have 5, a total of 11. Filling up the middle, we have 2 that we will place in our sigma bond coming from the sets of 2s. 2 go into our sigma antibonding. 2 electrons go into our sigma bonding from the overlapping p orbitals that are directly along the internuclear axes. Then we have 2 sets of 2, or 4, that are in our pi bonds coming from the 2p orbitals, and then 1 remaining electron goes into our pi antibonding. As a result, the bond order of NO would be, counting up the number of bonding electrons, 2 plus 2 plus 2 plus 2, so 2, 4, 6, 8, 8 minus 2, 3, 8 minus 3 is 5, 1/2 of 5 is 2.5. So we expect the bond order for nitrogen monoxide to be 2 1/2 order. Looking at another example, HF, hydrofluoric acid, we would be combining the 1s orbital from hydrogen with the 2p orbitals from fluorine. In this case, one of our p orbitals is going to have the direct overlap with the s orbital, creating the sigma bond. The remaining p orbitals will not be interacting with the hydrogen because the hydrogen does not have any additional orbitals to mix in to make molecular orbitals. So for HF, we will have 1 sigma bond, 1 sigma antibond that occur from the interaction between the 1s orbital from the hydrogen and 1 of the p orbitals from the fluorine. The remaining 2p orbitals stay as they are, unhybridized. as atomic orbitals that would be attached to the fluorine. Our total bond order for HF would be, we have 2 that are in our bonding orbitals. We have 4 in non-bonding orbitals, so these do not count towards or remove from our bond order, and then 0 electrons in our antibonding. So we have 2 minus 0 is 2, divided by 2 is 1. So the expected bond order for hydrofluoric acid, HF, is 1. For polyatomic molecules, those that have more than 2 atoms that are coming together, when the many atoms are combined together, the atomic orbitals of all of the atoms are combined to make a set of molecular orbitals. Those molecular orbitals are delocalized over the entire molecule. This gives results that are much better matches for real molecular properties than what we see with either Lewis or valence bond theory. For Lewis theory, when we are trying to depict molecules that have delocalization or resonance structures, we have to draw them as 2 separate structures with a double-headed arrow in between, implying to the reader that it is a combination of these 2. For the valence bond model, the bonding is occurring through the overlap of atomic orbitals, which means that our pi bonds are between our 2 atoms with a sigma bond in between, but that does not extend to the other atom. So in the case of ozone, our Lewis structure would look like this, having 2 different resonance structures. Our valence bond model does not adequately depict that our electrons are delocalized or spread out between all 3. For molecular orbital theory, you have the p orbitals from each one of the oxygens combining together to get an overall molecular orbital that expands and allows the electrons to be shared between all 3 of the oxygen. This gives a much better description of the properties that we see for things like ozone, O3.